We're on your first slide. Can you hear me now?
Yes, I'm on my first slide.
Okay. Yep. You're good.
You can see my screen now.
Yes.
Okay, very good. Okay, so now what I'm going to present to you guys, folks, today is VSLIMM, which is very small liquid metal cooled modular reactor, which is what we call it micro modular reactor. Modular means it's going to be fabricated, assembled, sealed in the factory, and every copy will be identical to the other copy. And it is designed to produce 1 to 10 megawatt thermal. So you say what you can do is 1 megawatt thermal. When you convert that to electricity at the 30% efficiency or 35% efficiency, the 1 megawatt thermal reactor unit will be enough for about 500 households, and the 10 megawatt will be about 5,000 households. This gives an idea about what kind of communities are we targeting with this kind of technology. So it is operates. It depends on the power level you operate at. If you design it to operate at 1 megawatt, it will last for 92 years without any refueling, continuously, 24/7. If you run it at 10 megawatt, then the lifetime will be about 5.6 full power year. Fully passive, no pumps. It operates by the effect of gravity. It has a redundant safety and shutdown feature. Redundant means you have more than one system that does the same function. So, there is no proliferation concern because it will, as I mentioned before, it will be assembled, fabricated, and manufactured in factory and sealed. So basically, the sealed unit will leave, and then at the end of life, the sealed used unit will come back. Okay, so there is no, it will not be open. We operate at temperatures and conditions where we use off-the-shelf material. So there is no R&D upfront required. It doesn't require any water for cooling. And this is now operate in a remote area where water is scarce. Then this would be a very good option that you cannot match it with any solar. But remember now, solar is still, is not a base load. And the wind as well is really, if the wind is blowing, then you have power. If it's not blowing, then you are off. It is portable. You can deploy it on a portable platform, as I mentioned, or you can have a number of units in a permanent site. It's a walk-away safe. What we call it is that nothing goes wrong with it by design. This means it relies on gravity and also other passive means. We use one of the passive feature is we use heat pipes coupled to thermoelectric. We call it liquid metal heat pipe thermoelectric modules. And this is take heat from the walls of the reactors and produce electric power independent of inside and offsite power sources. So no Fukushima kind of scenario will ever happen here, because you will have as long as you have heat, then you have electricity to take care of the critical functions of the plant. And the heat pipes, we have a number, they operate passively. There's no pumps, and we have multiple of them. So if one fails, it doesn't matter. If two fails, it doesn't matter. We design at 50% of prevailing limit, so you can lose 50% of them and they're still functioning. It operates in the decay heat, for nuclear reactors. Then after you shut down the reactor, then heat are generated by the reactive decay. We call it decay heat. So how you remove this heat? When this heat will be stored in the sodium, there is a lot of sodium inside the reactor vessel and would be eventually removed by natural circulation of air on the outside of the outside surface of the reactor vessel. It is cooled by natural circulation of sodium. Sodium has low vapor pressure, so it doesn't have a pressure vessel. So it operates slightly below atmospheric. The sodium, the in-vessel sodium represent a large energy storage, and this is good. And the reactor is designed what we call it negative temperature activity coefficient. So this means the hotter the reactor gets, the less reactive becomes, to the point that if we don't remove the heat, decay heat in a timely fashion, then we didn't cool the reactor in a timely fashion, then what will happen, the reactor can shut itself down without any active control, because if it heats up, it will shut down, and still hundreds of degrees below boiling point of sodium. It is inherently load following, so that if we talked about the change of the load, electricity demand on the grid, it will follow the load demand without active change in the reactor control within whatever the design limit we have, could be plus or minus 5% or plus or minus 10%. And I mentioned about the auxiliary power, it's a major advantage. And it could be, it is designed so that you can really operate it and control it remotely. It's modular, we talked about the module here. Now, how we modulate the power? Well, you're using the same reactor, the same everything, except there is a chimney inside the reactor that facilitate natural circulation. So if the chimney, the in-vessel chimney is 1 meter tall, then you operate at 1 megawatt thermal. If it's 2 meters tall, you can operate at 10 megawatt thermal. But the same reactor, the same fissile inventory. So you look at it as you having a tank of gas that carries certain number of gallons. If you consume the gas slowly, then it will last you for a long distance. If you consume it fast, it will last you a shorter distance. Okay, it could be deployed portable. This is a major advantage, and it's going to use open air energy conversion. So we use Brayton cycle with open air, and this is an advantage. This is why you didn't need any water to cool it. This picture here shows you where this is an 18 highway all the time, and this is the reactor. This is a sodium air heat exchanger. This is the turbo machinery, and this is the generators. But also we can have number of units deployed at the site. At site deployment, okay, this shows you here the at the site. This is the reactor here that you see. This is the VSLIMM. This is the reactor vessel, and this is the chimney. And this is the active core that generates the power, and they have a heat exchanger, the sodium air heat exchanger and downcomer. And of course, the sodium free surface inside the vessel will be covered by argon gas to prevent a barrier between any air leak into the here. This is a 6-foot person, so this will tell you an idea, give you an idea about the dimension of the reactor. This is the heat pipe. The representation how the heat pipe works. Heat pipe was invented by Dr. George Grover in Los Alamos in the early 60s, and since then it is really widely used in many industry. So basically, it is a pipe that doesn't have to be circular. It could be any geometry, and it is vacant on site except on a very thin working fluid saturated wick on the inside. So you heat it from one end, so the working fluid will evaporate and then transverse the length of the heat pipe to the other end where the heat is removed, and the heat is removed and supplied to thermoelectric module, which is fully static, passive, redundant to generate auxiliary power. This is just maybe too much information, but to tell you what that is, this is how the reactor core, when you cut through the reactor and look, it's comprised of a hexagonal bundle. Each one has 19 fuel rods, and some of them that you have, this red here has a poison rod that absorb a neutron for control. And we use, in the middle here, the hexagonal bundle here is fully filled with poison rods, and we use for emergency shutdown. So either use emergency shutdown or use the rods in the core here for control. Either one of them will shut down the reactor if you want to. And if neither of them work, or for whatever reason, which very, very unlikely, then if the reactor heats up, then the negative reactivity inherent into it is going to shut down the reactor. So target markets, well, this is designed to provide not only electricity, but also high temperature heat, because it operates at about 800 degree Kelvin. So we have high temperature heat that you can use it for many applications in oil refineries, hydrogen production, and in mining of minerals out in the boonies, as like aluminum and others. So there's a diverse list of industry that we have in our publication that you can use. So, and also this make it also very friendly with if you have it connected to a common grid with renewable like solar and wind, because during the day when this renewable energy is fed into the grid, then you can switch to the high temperature process heat production, and at night you can switch to electricity full time or in between. Potential market, as I mentioned earlier, remote, very remote, that have no access in the boonies there, in Alaska somewhere, or in New Mexico, Arizona, the Native American communities, in arid area, so you didn't need water, so it could be arid, you didn't need water there, or in coastal region where you need to use energy, thermal energy or electricity for water desalination, another thing, or island nations as well. Advances basis for the military or military operation where you didn't have to carry a lot of oil tankers for the troops to provide energy there. So one reactor like that will provide a lot of energy. Or in areas where, as I mentioned, Alaska was covered with ice year round, so you didn't have access to outside sources except flying in your fossil fuel. And also this will be a very good choice for disaster relief areas or effort, where you truck the entire plant, or you fly the entire plant, or you ship it by rail or on a barge to the area to provide disaster relief. You didn't have to connect anything, it just is ready to go. Also for minerals and natural gas explorations in remote areas, where they have to truck in all their energy needs. So this one would be great there for 5 to 92 years, it depends. You can have multiple units for deep sea exploration and seawater desalination. This is just a few examples there. It is low risk investment. This is very important now that Wall Street see that this investment has high potential, low risk. Low risk is because there is no Fukushima-like accident. There is no core meltdown like accident. There is no 3 Mile Island like accident. There is no anything like that by design. It operates passively, so it's rely on gravity. So as long as life exists, gravity exists, then it operates. It doesn't have a pressure vessel. It operates with below atmospheric, slightly below atmospheric, so you didn't have to worry about, having a pressure breach or something like that. It's compatible with renewable on a common grid, no or little R&D, because we're using off-the-shelf technology. We're using like HT9 steel for structure. We're using uranium nitride for the fuel, and using sodium for coolant. It operates for a long time, as I mentioned before, and you have flexible deployments. And now, if you put it in a site in a populated area, then the diameter evacuation zone is very small, 2 miles, 1 to 2 miles. This is a major advantage for license if you try to use, for example, a number of these units. The other thing also is unit cost is low. Like, say, for example, PNM would like to entertain this technology. So instead of going for 1,000 megawatt plant, which is much more than they need, like we have for Palo Verde, for example, they have to share the ownership with Arizona and other states. Here, the units will cost less than $300 million. It will be installed and connected to the user in about a year to year and a half. So they start getting revenues, and when they install, they start working in the second unit. So the first unit is producing revenues. And instead of investing $6 to $10 billion in the large power plant, and then wait for 5 to 8 years before it's really connected to the grid, before you get in the revenues, and the bank is cranking interest during that period. We expect our estimate is that the first of a kind unit, the first unit that will be built because of R&D and all the licensing and so on, will cost about 600 to 800 millions. But after that, we feel that the cost per unit will be about 300 million. You say, okay, for the 1 or the 10 megawatt, for either of them, because as I said, the only difference is really the chimney height. So if you want to go with the 10 megawatt, you can go, but you're going to, unit will last for 5.6 years. If you go with 1 megawatt unit, then it will last you for 90 years plus. There is no non-proliferation issues or end-of-life handling. Non-proliferation means that no one can fool around with this reactor because it will be sealed all the time. It will sealed and manufactured fully in the factory, so there's no component be transported in the process. And at the end of life, our work shows that you can leave it on site for about a few months, then the radioactivity will decrease to the level that could be safely transported back to the factory. And and also, since you didn't have any refueling, there is no any storage of fresh fuel or use the fuel inside. So it uses, what we call it high assay low enrichment fuel, which is really recommended by the DOE and NSA. The uranium fuel has 16% enrichment. So the market is very promising. There is a lot of interest in the last 5 years worldwide in small and micro reactors. Okay, all over the world. Not at the US, there are a number of concepts being developed. Micro here is really for about, if the reactor produces less than 40 megawatt thermal. A small reactor is really up to about 300 megawatt thermal. These are arbitrary classification. There is no any science or logic in that. It's just this is a classification. Now, the US industry, there are a number of concepts, as I said, about close to 10. Some of them are very close to licensing and operation. They generate electricity between a few megawatt electric to maybe about 50 megawatt electric. There is one option that can produce up to a couple of hundred megawatt electric. But none of these are portable. and have the feature that VSLIMM MMR provides. Again, summing here is that it's the feature that we have here is unmatched, and the redundant operation and safety features as well. It's fully passive, long life, provide auxiliary power independent of on-site and off-site power. This is a feature that doesn't exist in any power plant in operation at present, or in many of the published work on the concept being developed. It's fabricated, assembled, and sealed. It could be deployed on a portable platform or in cluster at named site. Now at the site will be installed below the ground using isolation bearing, so it will not be protected against any missile attack or any earthquake. No inside storage of either fresh or used fuel, no water cooling required. It's scalable between the 1 and 10 megawatt. We have a SLIMM concept, which invention also through the Rainforest innovation, which can produce up to 100 megawatt thermal, and you have many of the common features with VSLIMM. We have independent safety system for reactor control for emergency shutdown, and if neither of them work, then we have the negative potentiality feedback that will shut down the reactor, and has a potential for remote operation control. So we can put it on the site and we control it remotely. Next step, explore industry interest to license, because this is not this is a major investment. And what they will do is they will need the industry capabilities is beyond the university or academic capability to advance, to start getting in the hardware. We have done everything that you do in terms of design, paperwork, analysis, using the state of the art, but you need to go to actual hardware and fabrications. There will be some issues that has to be resolved. And of course, this will require venture capital, and there are matching funds now at the present time at the existing concept being developed to secure commercial license eventually. Funding requirements, well, it will take, in my estimate, about 600 to 800 million to get the first of a kind unit, and about 5 to 8 years to complete that. And subsequent unit will cost less than $300 million. This is give you some chart. You didn't have to. I will explain that to you. Is when these lines intersect with the horizontal axis here, this will tell you the lifetime. So at 10 megawatt, the operational life is 92 years, and at 1 megawatt is about 5.6 years. But you can have a chimney between 1 and 2, so you can operate at different power levels, and this will give you the lifetime. The figure at the bottom here, it shows you is what happened. What is the radioactivity at the surface of the reactor after shutdown? Look to the blue line, and the dashed line here. This is the background. This is the safe limit for transportation. As you see here, is if you leave it in place for 103 days, which is about less than 3 months, then you'll be able to take it from the site and move it to the factory.
And I think we're going to have to move on.